off with a little review, of some stuff that we talked about last class, specifically the motion, kinetic energy of gases, and how the velocity relative to kinetic energy, how those two parameters relate to each other. So here we have a question that says that the average kinetic energy of all gas molecules at the same temperature is the same, right? And that's what we've always said, that temperature is a measurement of motion of the molecules. And we introduced last time that 1/2 mv squared is the way that we can measure the motion of the molecules. So then the question is, compared to lighter atoms at the same temperature, heavier gaseous atoms on average would move, and we want to think about if we can get this answer. All right. Jace, do you want to give us an answer for that one?
Would they move at the, I think the smaller molecules have a faster velocity, but because the mass is more, the kinetic energy would be the same?
The kinetic energy would be the same, that's right.
I would say that they would move lower, but then the kinetic energy is the same because their mass is greater.
That's right. So the question here recognizes or indicates that the kinetic energy is the same for these different gases. For any gases at the same temperature, they all have the same kinetic energy. But now we're reminding us that they don't have the same velocity. That, yes, larger molecules of gas will move slower. Very good. Okay. And we also said that we could kind of actually identify relative rates of movement if given enough information about the comparison of two gas molecules. So if we said we observed bromine effusing, does anybody remember what effusing means as opposed to diffusing? What does effusing mean, Harry? Do you remember?
Is diffusing when gas molecules move through a small, tiny space into another empty space?
That's right, into a vacuum. That's right, that's effusing. And what do we call it when gas molecules, I open up a container of perfume, right, and the gas molecules slowly go out into the room. What's that called, Harry? Not effuse, but what? Diffused, right, with a D. And they have to diffuse through other molecules of air, gas that are in the way, right? Okay, so bromine effuses at 5 centimeters per second. If a sample of an unknown gas travels at half that speed, 2.5, right, what's the molecular mass of that unknown gas? How would we set this up, Brielle?
I'm not 100% sure.
Well, they would both need to have the same kinetic energy. Is that true?
Yes.
Same kinetic energy. So could we say that the 1/2 mv squared, if that was for our bromine, right, would have to be the same kinetic energy as the 1/2 mv squared for whatever the other gas is?
Mm-hmm.
All right. And if we knew something about the, let's see, what do we know about? If this is our bromine side, and this side, we don't know what this gas is over here. Do we know the V for this side, Brielle?
Yes, it's 5 centimeters.
Okay, we know the 5 there. Do we know anything, do we know the mass maybe?
Yeah. When you just do the mass of bromine times 2.
Yeah, okay. So let's see. Let's bring over our periodic table. take a look here. What do we got? Where are we at? Oh no, what happened? There we go. Why isn't it zooming in? I thought I could zoom in before. Oh, maybe I have to hold that. Okay, so get over to bromine. Where are we at? 79.9, so it's essentially 80 times 2, 160. Okay, 160. Is it okay if I cross off the 1/2 on both sides, Brielle? You see why I do that?
Yeah, because they'll just cancel each other out.
Yeah. Okay, so then I can hopefully solve for what? Do I know? What do I know? What do I know on this side, Brielle?
That it's half of 5, so it's 2.5.
Okay, 2.5 squared. And then should I be able to solve for the mass of the other gas that way? Is that going to work?
Yeah. Mm-hmm.
All right, so 160, 5 squared, I know is 25, divided by 2.5 squared. Where's my calculator? 2.5 squared. Where are you at? Square button. There it is. 6.25. So 160 times 25 divided by 6.25. Did I do that right? 640. Wait, was it 160? Yeah, because it was 80, right? 80 times 2. 640. So the mass is larger. Does that make any sense, Brielle? Should the mass have been larger?
I mean, yeah, because if the velocity is faster for the lighter atom, then it makes sense for the velocity to be slower for a heavier atom.
Okay, all right. So we have some confidence that we're in the same or the right ballpark. Okay, so we were right, 640 grams per mole. Okay, good. So in the slide here, they start with this equation where there's the ratio of the rates of either effusion or diffusion, the rate of any gas, right, compared to the ratio of their molar masses, square root of it. But that's essentially this same equation here, 1/2 mv squared of one gas being set equal to 1/2 mv squared of the second gas. Okay, so from that we can answer, well, with that information, a little bit more review here. Sarah, what do you think? Which of these two flasks has the have a greater average kinetic energy? It looks like I have two flasks here. One has carbon dioxide, one has helium. All right, what do you think, Sarah?
So they're at the same temperature, so they have the same kinetic energy, right?
All right, that's right. So we would say, which flask of molecules has a greater kinetic energy? Neither. They have the same kinetic energy. Very good. Now what about this one? Which flask has molecules that are moving faster? Sarah, go ahead.
That's also neither, right? They're the same.
Okay, so we decided that, is it possible for two systems that are at the same temperature, same pressure, same volume, two different kinds of gas molecules, right? Is it possible for them to have the same kinetic energy but different velocities? Sarah?
Yes.
Yes, it is, right? So if their kinetic energies are the same, the only time they would have the same velocities is if they also had the same masses, right? So in this case here, we're told basically that they have the same kinetic energy because they have the same temperatures, but that doesn't mean that the molecules of the different flasks are going to be moving at the same velocity. They'll have the same kinetic energy, but which one, based on basically our previous experience, right? Here was bromine with a mass of 160, and then we compared it to some unknown gas with a mass of 640, right? which one of these had a faster velocity, faster velocity, Sarah?
The bromine had a faster velocity.
That's right, because it had a lower mass, it had a faster velocity. So in this question here, helium is going to be the one that has the higher velocity because it has a much lower mass than the carbon dioxide. Does that make sense, Sarah?
Yes, that does make sense.
Okay, good. All right, very good. So there's some review. Here's another question we could answer. I'll leave that one to you if you want to do that one, but that's a good enough